The first edge section method we will talk about is the gradient operators. The principle on the gradient operators can be actually shown by just looking at the gradient of a function in 2D. Let us assume that we have a continuous image that's given by f of x comma y. So f represents the image intensities, x and y represents the spatial coordinates. The idea is to locate f's steepest slopes using the gradient magnitude. The gradient magnitude simply is given by the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared summed and then square root. The gradient magnitude measures the slope of the steepest direction at a given point in the image. And I'm sure you've actually seen derivatives and gradients before. So this is their application in images. And it's easy to see that actually the gradient really gives you the steepest change. You can prove it simply by saying that, you know what, let's find the derivative or the change in f in one v direction that's given by cosine theta and sine theta in 2D. The change of f in that direction can actually be given by this formula. So the gradient of f dot product with the v. If I take the derivative of this with respect to theta and maximize it, I will find that the extremum theta is given by the arctangent of the ratio of the partial derivative with respect to y over partial derivative with respect to x. This leads to the magnitude of the maximum change to be given by the gradient magnitude given here. Now, the idea here is edges in an image should reflect the edge profile that we've seen before, so they should attain the highest gradient in the image. But all this discussion was for continuous domain. So how do we implement it in discrete images that are already digitized? The gradient magnitude is a nonlinear operator, so it's difficult to directly implement it. However, the individual derivatives, the partial derivative with respect to x and the partial derivative with respect to y, are linear operators. They are actually linear and shift invariant operators. That means that I can approximate them using convolutions. The simplest approximation would be to approximate the finite differences. So I would approximate the derivative with respect to x by a convolution kernel that looks like this, which basically finds the difference between the two pixels that are neighboring each other in the horizontal direction. Similarly, the partial derivative with respect to y can be approximated using a convolution kernel given like this. So it finds the difference between two pixels that are one above each other. And these are convolutional kernels, meaning that I would take an image and I would simply use convolve the image with these kernels. That would give me the derivatives in the x and the y direction. And once these are computed, I can approximate the gradient magnitude and the direction of the maximum change using the results at each pixel. While these convolution operators are easy to explain, interpret, and also implement, they are prone to noise. If you think about the noisy profile that I've shown before, if I take such a derivative, it will really be noisy. So due to that, if I apply these convolutional kernels on the image directly, I will see lots of spurious high derivatives. Instead, we want a tool that will not be prone to noise. So it should be smooth in one direction and take the derivative in the other direction. One such operator that's used quite often is called the Sobel mask. It's also a convolutional kernel. So instead of convolving the image with minus and 1 to find the x derivative, I would convolve the image with this operator to find the x derivative, and with this operator to find the y derivative. Notice that it's actually quite intuitive. So I have negatives here, I have positives here, so I actually find the difference between these pixels, somehow weighted by 1 to 1, and this weighted sum of these pixels. And for the y derivative, it's the same thing. So in these cases, one mask primarily computes the derivative in the horizontal and in the vertical direction results. And again, to find the magnitude gradient, I simply combine the results, so taking the square root of the sum of their squares at every pixel, and that will give me an approximation to the edge strength in a sense. And I can also take the arctangent of their proportions to find the direction of the maximal change. An important point in the Sobel masks is that they're separable, meaning that if I look at, for example, x derivative convolution, I notice that this can be really divided into two. One part is this guy, -1, 0, 1. One part in this one, 1, 2, 1. So the horizontal and the vertical convolution kernels. And looking at it like this, something becomes very apparent, the principle behind Sobel mask. You see that this operator here looks very much like the derivative operator we've seen before. Instead of having a 1 here, it has a 0 here, and the 1 is shifted, but this is basically the derivative operator. And this is the binomial filter. So we've seen this before when we studied binomial filter, that this was actually quite a good filter to smooth images. And indeed, if we look at the power spectrum or the modulation transfer function of the Sobel mask, we see something like this, where this is the direction where the smoothing happens, and you can see that it's actually a very nice low-pass filter that actually only retains low-frequency components in this direction. And in this direction, it's a bandpass filter that actually takes the derivative. If I look at the results of this is the results that I get. So I have the image here. Here, I have the derivatives in the horizontal direction, and here I have derivatives in the vertical direction. When I combine them with the square and square roots, I get the magnitude as given here. And you see that that's actually quite nice. We see that actually despite the various noises here, and despite these pixelation artifacts, I don't really see them in the derivative image. Well, that's because actually the smoothing really gets rid of them. So I can concentrate directly on the edges. So the gradient magnitude responds well on the edges. Although it's nice, the results of the gradient magnitude is far from perfect. In the ideal case, what we would like is, we would like one line thick pixel edge around the object without any gaps that clearly identifies the object. But here we have gaps. For example, if you look at here, you see that the boundaries are actually not there. We have several pixels thick at places. Here, there's a lot of pixels that are identified as edges. And while some edges are strong, others are weaker due to the changes in the illumination. So it's far from perfect. However, this is actually a good start, and we'll see that this is used for further edge detection methods. And the idea here is the Sobel masks are really the optimal 3x3 convolutional filters with integer coefficients for step edge detection. And this will become clear as well as we move forward. Okay, this actually brings us to the second topic, which is our second approach for edge detection, which is the zero crossings of the Laplacian. In the first approach, we said that we want to detect the highest gradient areas or highest derivative areas in the edge profile. Here we want to compute the inflection points. So we consider that edge really should be at an inflection point in a profile. And inflection points can actually be computed as the zero crossings of the second order derivative. In 2D and also in 3D and higher dimensions, the second order derivative operation for this task is actually approximated or is actually implemented using a Laplacian operator. So that's the second derivative of the image with respect to x plus the second derivative of the image with respect to y, and their sum should be 0 at the inflection points. Now, this is actually also a linear and shifting invariant operator and can be implemented using a convolution. And it's also an isotropic operator, meaning that it doesn't really prefer any directions. The discrete convolutional kernels that approximate Laplacian are multiple. Here I actually show only two of these 3x3 kernels. If I look at the modulation transfer function of this guy, it's given like this, just for completeness. What's more interesting probably is actually their modulation transfer function shapes for both of them. Now, the zero line is actually given by here, in this case. So you see that actually the Laplacian operator is indeed a high-pass filter. It really kills the low-frequency components and only passes the high-frequency components. And the high-frequency components are reversed in sign, but that's okay. In this case, it's the same thing. I have a larger, a different kernel with the same properties. It basically kills all the low pass frequencies and passes the high pass frequencies with the phase reversal. When we implement the zero crossing or the Laplacian operator, we have to be careful about the noise. We said that the first order derivatives are very sensitive to noise. Well, here we're looking at second order derivatives. So the direct implementation of the Laplacian operator can be really detrimental. It actually will produce a lot of spurious edges in the image. So it's actually usually combined with a smoothing operator, particularly with a Gaussian. So first you would take the image, you would convolve the image with a Gaussian filter to get rid of the noise as much as possible, and then you would apply the Laplacian operator, and all in terms of kernels and convolutions. And because we know that the convolution associative operator, actually I can change the order and say that, you know what, let me combine the Laplacian operator with the Gaussian and call this a single filter, and with this single filter I should convolve the image to directly get the result. And this filter has many different names. It looks something like this, and because of the shape, it's often referred to as the Mexican hat filter, or the Laplacian of Gaussian filter to be more descriptive, or the method that goes on. Now, you can actually implement this using really taking second derivative, Laplacian operator of the Gaussian filter, or another way of implementing it is actually you take two different Gaussians of different standard deviations and simplifying the difference. And that actually gives you a difference of Gaussian filter that really well approximates the Mexican hat. If I apply the Laplacian operator or Laplacian Gaussian operator to the image that we've seen before, this is the result that I get. Now, what was I supposed to look at is actually the zero crossings of this image. And the zero crossings look something like this. So indeed, I get 1 pixel thick changes. And this is natural because I'm actually only looking at the pixels that are really at the zero crossing. So they're only 1 pixels for each location. Although in this image they look like they're not closed, but when you apply it, it's actually you really get closed contours. So the reason why it doesn't look closed is the rasterization of the image. Yet these results are not convincing at all. I have so many spurious artifacts here. I mean, here, look at, even though we've actually smoothed the image with a Gaussian, we still get so many edge patterns in this homogeneous area. And that's normal because even for small variations in intensities, if there is any zero crossing, this operator will pick them up and show them as edges.